Hello and welcome. In this video, we'll be going over when and how to perform a Wilcoxon signed rank test. Now, the first thing to note is what this test is for. The Wilcoxon signed rank test is used to test for a difference in population means of two dependent samples. This means that each sample will have the same number of observations, and those observations will be paired, or dependent on one another. A classic example of this would be the before and after analysis. To use this test, our data must be of an ordinal level or higher. That is, it must be data we can order or rank. One key thing about the signed rank test, however, is that it does not have to assume a normal distribution. This makes it useful in cases where parametric dependent sample tests, such as a paired t-test, cannot be used. Our basic steps to perform this test remain the same as most tests we've seen so far. We start by stating our null and alternative and determining a level of significance. Then, we'll find our critical value and use that to formulate the decision rule. Next, we'll solve for our test statistic, and finally, we'll evaluate it with our decision rule and interpret what the results mean. To help demonstrate from here, we'll use a follow-along example. This example is taken from a class assignment I've had to do for our stats class. So, a random sample of 15 participants in a weight loss program showed these weights before and after participating in the program. These can be seen to the right. Without assuming a normal distribution, perform an appropriate test to see if the program is effective. Use a 5% significance level. We are going to use the Wilcoxon signed rank test for this, but let's go over the criteria to just double check that we meet all the criteria to use this test. So, 1. Tests a difference of population means. We certainly intend to. We're looking at two different population means. One is the average weight before, the second is the average weight after. And we want to see if there's a difference, so we are comparing them. Our first criteria is met. 2. The samples must be dependent. In this case, yes, each pair of samples is linked to one participant. We have a before for participant 1 and an after for participant 1, and the same for 2 through 15. So our samples are dependent on one another. 3. Is our data of an ordinal, interval, or ratio level? It is. It's numerical values which we can count, and therefore it will meet that criteria. And 4. Does not assume normally distributed populations. As mentioned in the question directly, this is in fact the case. So, we can use a Wilcoxon signed rank test. Let's start that now. Alright, so our first step is to determine the null and alternative. To do this, let's think about what we're looking for in the question. We're trying to determine if the weight loss program is effective, and for that to be the case, our average weight after must be less than our average weight before. Or, in other words, the population mean after must be less than the population mean before. This result does not have an equals in the operator, and so this will be our alternative in the statements, as so. The null will then cover the rest of the possibility spectrum. If our mean weight after is not less, then it must be equal to or greater than before. We are given our significance level of 5%, and as we can see from the operators in our null and alternative, this will be a one-tailed test. The next thing to do is to find our critical value. This is determined by our degrees of freedom and our significance level. This is a one-tailed test using a 5% significance level, so we'll be looking in this column for our eventual critical value. Our degrees of freedom are equal to the number of usable pairs of observations. We have 15 such pairs. However, for the Wilcoxon signed rank test, we must omit any pairs that experience no change. A quick look shows that we have 2 such pairs in this sample. Once they're omitted, we'll be left with 13 usable pairs, and so our degrees of freedom is equal to 13. Therefore, we will look in this row. Our table now shows that our critical value is 21. When using this test, our rejection region is going to be below this value, which we could actually infer from the fact that our critical value increases with our degrees of freedom. Anyway, avoiding that tangent, we can formulate our decision rule now. If our test statistic, t, is less than 21, our critical value, then we will reject the null. Now we're on to calculating the test statistic, and here are our steps to do that. First, we'll find the difference between each pair of observations. Then we'll take the absolute value of each difference, and we will rank our paired observations from lowest to highest, using an average rank for tied pairs, which we'll go over in a minute. After this, we'll assign our ranks to positive or negative signs and take the sum of each, so the sum of positive signs and the sum of negative signs. Finally, we'll find our calculated test statistic as the lower of these two sums. Here's our data again, and we want to find the difference between each pair, so that will be before minus after in each case, and we'll list it along with its absolute value. So our difference here we see is 1 for participant 1, and so the absolute value will be 1, obviously. For participant 3, our difference is negative 4, and so the absolute value will be 4. Again, note the two pairs that have no difference here. We will be omitting them going forwards. I'm going to sort this data with Excel to make it a bit easier to rank now, and then I'm going to assign ranks to each participant. There. Our two no-change pairs are ignored, and then each pair is ranked from smallest to highest difference. Participants 1 and 3 have an equal difference and are tied for rank 1 and 2, so I averaged the two ranks and assigned each a rank of 1.5. Similar rank averaging has been done as necessary down the line, mostly ranks 1 through 9. Now, we'll assign each rank to either a positive or negative sign, which is determined by the sign of the differences found. We have 9 positive differences, as indicated by the green stars, and we'll move all of these to the positive rank column, like this. These are our results, which have experienced a weight loss of some quantity. Our remaining 4 differences are negative, as shown with the red stars, and we'll move those over too. To find our test statistic now, we'll sum each of the 2 columns, like so, and use the lower of the 2 as our t-value. So t, in this case, is equal to 22. Recall that our decision rule is, if t is less than 21, reject the null. T is 22 in this case, which is not less than 21, therefore we fail to reject the null. The last thing we have to do is to interpret what this means. Here again are our null and alternative. Since we fail to reject the null, we instead reject the alternative. So we find that there is no significant weight loss effect from this program. Of course, we've only done one test, so we can't conclude anything definitively, but we might say that, based on this sample, at the 5% significance level, we cannot conclude that the weight loss program is effective. And that is the end of our Wilcoxon signed rank test. If you feel like you need a bit more practice, I would advise anyone watching this to go back and watch this video again, and try and do it yourself, and then go along with the steps to make sure you're doing everything correctly as you go. I hope this was useful, and thank you for watching.